Chapter 14, Salts. So we're going to have two different examples in this video. One of these salts will act as a base and the other will act as an acid. So first we have KC2H3O2. Now we know that this is a salt because we have a metal plus a polyatomic ion. If you have a metal plus a nonmetal, or if you have a polyatomic plus a nonmetal, all of those would be classified as salts. So basically you just want to have a metal or a nonmetal involved in here, a cation and an anion. So step one is going to be, as usual, identify the major species. So in this case, we have KC2H3O2, which I'm going to point out is just potassium plus COOH. Oh wait, is that right? No, sorry. Let's do that. Potassium plus our acetate polyatomic. Let me just make sure I got that right. 2 carbons, 3 hydrogens, 2 oxygens. Yep. Okay, and we know that this is a salt, which means it is a strong electrolyte. Okay, cool. So now that we've done that, step 2 is to write out the reaction. So writing out the reaction when you have salts is slightly different than usual, so make sure you pay attention to this. First, you're going to write your salt in your reactions. I'm going to write it out where you can see the ion. And since it is a strong electrolyte, what kind of an arrow would you use? A one-way arrow. And we're going to show our metal separating from our polyatomic. Now here is something that you want to take note of. I'll use black for my extra little notes. The cation from a salt does not affect the pH. However, it's what would I call this? Other ion. There should be a word for that. Maybe it'll come to me later. This one does. Now, if we had the reverse of this, like in our next example, we have ammonium chloride. Now here in this one, our chloride is not going to affect our pH. So let's see. Let's take what is going to affect our pH, our acetate, and we are going to show that this becomes CH3COOH, becomes acetic acid. And so we can see, since it had that negative symbol at the beginning, it is willing to accept a hydrogen. So if it is accepting hydrogens, that would mean that it is acting as a base. Now, if you'll notice, there are no hydrogens in our equation for it to accept, so I'm going to add water into here to show where it's getting that hydrogen from. And since it took a hydrogen from that water, what is left over? Hydroxide. So I'm going to put a little star next to this. This is the equation we're going to use. Alright, so now step 3 will be to do what we usually do, which is write the equilibrium expression. Do I need to do a dilution on this problem? No, I don't. It's not being diluted. So since this guy is accepting hydrogens, am I going to write a Ka or a Kb? I'm going to write Kb because it's acting as a base. So I'll put my products, hydroxide and acetic acid, over my reactants. I'm not going to include water because it's a liquid. Now, we don't know what Kb is equal to. We were given Ka. Do we have a way to change Ka into Kb? Yes, we do. We know Ka times Kb is equal to 1.0 times 10 to the negative 14th. Oops. So I'll say, okay, 1.76 times 10 to the negative 5 times Kb is equal to 1.0 times 10 to the negative 14th. Oops. 14th. So I get a Kb value of about 5.7 times 10 to the negative 10. And I'm going to take that number and I'm going to insert it into my equilibrium expression. So that'll be 5.7 times 10 to the negative 10. Okay, great. Moving along, step 4 will be, well, we want to be able to solve for the pH. And if we want to solve for the pH, we need a concentration of hydrogen ions. My equilibrium expression doesn't have hydrogen ions, but what does it have that if I solved for it could give me the concentration of hydrogen ions? We have hydroxide ions, and I know I can figure out the concentration of hydrogen if I know the concentration of hydroxide. So our ultimate goal is to get the concentration of these hydroxides. So that means that I need to figure that out, which means I need an ice chart. This unit, you have a lot of different tools you can use, and you want to just figure out which tool you need to use for which problem. So ICE in my equation. As I've said before, I like to write water up here. Oh, I just realized there's something I need to fix up at the top. What kind of an arrow do I need when I'm dealing with acetate and acetic acid? Are these strong or weak? They are weak, so I need to use a double arrow. Another way to remember which equation we're actually going to use in our ice chart is you always use the equation for the weak substance. That's another way to remember it. Use the equation for the weak substance. And we know that acetate and acetic acid are weak, so that's why I'm using this equation. And that's why I need this double arrow. So I'll have CH3COOH, and I have my hydroxide. And remember, we don't include liquids, so that's gone. All right, initial concentration. Well, I know I have an initial concentration of, what do I know? Well, I know my initial concentration, I'm going to use a different color here, of my salt. I'm going to underline it. I know, oops, wrong color. I know the initial concentration of this salt. I know it's equal to 0.10. And so I know, since it's 1-to-1 with potassium and acetate, that I have an equal concentration of my acetate ion. So over here, I'm going to use that concentration, 0.10. And I know at the very beginning it has not fallen apart at all, so there's nothing there. I don't know anything at equilibrium, so those become x's. And I end up with 0.10 minus x, x, and x. Okay, so let's scroll down a little bit. So now that I have that, I'm going to plug into my equilibrium expression. Because I want to figure out some concentrations. So let's see. I know that x squared over 0.10 minus x is equal to 5.7 times 10 to the negative 10. I'm plugging my x's into my KB equation up above. So knowing that, I'll end up with x is equal to 7.5 times 10 to the negative 6th. And I know that this is equal to the concentration of my hydroxide ions because x is equal to my hydroxide concentration. So now I get to figure out the pH, which was the whole goal of this. So let's see how to do this. You have different ways you could approach this. I'm going to solve for pOH and use that to figure out pH. So that's equal to, oops, I didn't write my actual step. We are solving for pH. Okay. So pOH is equal to the negative log of the concentration of hydroxides. I need a little more room than this. So that means that that's equal to the negative log of, what was it, 7.5 times 10 to the negative 6. So my pOH comes out to about 5.12. Remember, I want 2 sig figs. It's going through a log, so 2 sig figs only count after the decimal. So the 1 and the 2 contribute to my sig figs. Okay, well, I know that pH plus pOH is equal to 14. So 14 minus my pOH is equal to 8.88. That you could think of as 14.00. There. Okay, that's it. That's my pH. So I can box this up. That is my answer. And something that's good to note is that salts will always have a mild pH. You're always going to get a mild pH from a salt. So that is problem 1. Now let's go back up to the start and try it again. If you'd like to try this without me, you could just, oops, that should be step 1. Just keep in mind that this guy is going to be acting as a base. This will be acting as a base, I believe. Wait, no, other way around. We just solved one that was acting as a base. This one will be acting as an acid. This will act as an acid. Okay, so here we go. That color difference isn't enough for me. Okay, there. Step 1 will be, as usual, identify major species. So here we have ammonium chloride. And we know that this is a salt. We have a polyatomic with a non-metal. We've got a cation with an anion, and that makes it a salt, which is a strong electrolyte, which is helpful to know. So what we're going to do now is write out the reaction. We have to do this in 2 parts. First, we take our original species and we split it up. It is a strong electrolyte. Use a one-way arrow. Show ammonium plus chloride. Now that we have that, we're going to take whatever is the weaker substance and we're going to write an equation for that. And we know that ammonium reacts to form ammonia, so we're talking about weak stuff here, whereas chloride, if we were going to react that with water, we'd actually end up with HCl, hydrochloric acid, which is very strong. So we're not going to use that. We're going to use our ammonium. So we'll take ammonium It is going to be weak, so use that double-sided arrow, and it's going to drop a hydrogen and form ammonia. And that's just something that we know ammonium does. Okay, cool. So now we need to write out the equilibrium expression. Step 3, oops, sorry about that. Write out equilibrium expression. One day I'll go back and redo these videos without all my oopses. So ammonium is releasing a hydrogen. So is it acting as an acid or a base? If it is releasing a hydrogen, it's acting as an acid. So I need a Ka. I'll have H plus NH3 and NH4 plus. Now this problem did not outright give me a Ka value. I have a chart posted on Canvas where you could print out a list of values, and from that you'll be able to find ammonium has a Ka of 5.7 times 10 to the negative 10. These are not values you have to memorize, you will be given them. So now that I have that, the goal is to find pH. I could find the concentration of my hydrogen ions through an ice chart. So let's do that. I'll have NH4 plus. By the way, if you chose to include water in your equation, you would still get the same answer. You would have had ammonium plus water reacts to form hydronium plus ammonia. That would have been perfectly fine. Nothing wrong with that. I just didn't have to include water because all of my hydrogens and everything was accounted for. Okay, so same as last time, I know that there's a 1-to-1 ratio between my ammonium chloride and my ammonium, so that means I know my initial concentration is 0.10 molarity, and I know I don't have any of these yet. I don't know any equilibrium values, so this is going to just be x. So I end up with 0.10 minus x, x, x. I will now plug it into my equilibrium expression. And oh dear, I just realized I left something out of the last one. Okay, we're going to do it here. So I will have x squared over 0.10 minus x is equal to 5.7 times 10 to the negative 10. Now, oh no, last time, here let's just look across. I just said, oh, this is x. The way I solved that, I'm just backing up a little bit, was by assuming x is small. And if you caught that, good for you. If you didn't, it's okay. I don't blame you. So I assumed x is small, and so I ended up getting rid of this x here. That went away, but I have to prove that that's okay, so I need to show that 7.5 times 10 to the negative 6 over what it's being compared to times 100 is less than or equal to 5%. So let's see what that came out to. 7.5 times 10 to the negative 6 divided by 0.1 times 100 equals a very small number. So we're good to go. 0.0075 is less than 5%, so we're okay. So let's not forget that step this time around. I want to assume x is small, and I can do that because my k value is small. So that means I can get rid of this x. So I end up with an x value of 7.5 times 10 to the negative 6. Well, that's interesting. It's the same number we ended up with last time, except this time this is representing our concentration of hydrogen ions. Now I have to make sure that that assumption was valid, so that means that 7.5 times 10 to the negative 6 over 0.10 times 100 must be less than or equal to 5%. And based off of what we just did, since it's the exact same numbers, I could say, yep, we're good. Great. So now that I have that, I can solve for my pH. And I know that pH is equal to the what? Negative log of the concentration of the hydrogen ions. You are given basically all of these equations, so life is good. 7.5 times 10 to the negative 6. So the pH in this situation is equal to 5.12, which is pretty mild. Not that far away from 7, just like last time, 8.88, not that far away from 7. So there you go. That is how you deal with salts.